So we've been studying continuous data and looking at the probability density functions that you get when the data is continuous. Now, this brings us to the normal distribution, and if you study biology, you've probably come across this already. It's called the normal distribution because it's just so normal. It's found all the time in nature. So a lot of the time when we measure things, what we find is that it's really normal to be normal and it's really unusual to be unusual. So looking at an example, if we were to say measure the height of all 18-year-olds in Australia and then graph the relative frequency of those heights, if we have the heights going along the x-axis and the relative frequency of those heights occurring, we could also call that the probability that any one person selected at random is any of those heights. We're going to find that most people are clustered around the mean, and that's because most people are going to be what we consider normal. It's going to be a symmetrical distribution because we've got just as many really tall people as we have really short people on the whole. And you'll see that as you get further away from the mean, the chance of being really, really tall or really, really short gets smaller and smaller. Now, this happens when you measure all kinds of things. So looking out the window for inspiration, I can see a lemon tree. If I was to take all of the leaves off that lemon tree and measure the length of them, then I'm going to find that the leaves are probably based around a normal distribution. If I took all of the lemons off the lemon tree and weighed them, I'm probably going to find that there is a normal or mean weight for lemons on that tree. And there's going to be the odd lemon that's really heavy and the odd lemon that's really light, but generally most of them are going to be very close to normal. So the features that we need to write down of these distributions, they're found a lot in nature. That have a symmetrical bell shape. I'm not really sure why they call this a bell, but I suppose an old-fashioned bell looks something like that. Now, most scores are near the mean. We've discussed that. And the mean is the maximum turning point. That seems fairly clear. And the chance of a value occurring depends on its distance from the mean. That seems also obvious. Now, this last point needs consideration. Each normal distribution will look a little bit different. It's got this same basic shape, but it might be, say, taller and steeper, like this purple one here, or it might be shorter and flatter and more spread out. What causes it to change shape? Well, different means will cause it to move along. If we have a mean that's higher or lower, it's going to translate from side to side. But to change the actual shape or to change the dilation, we need to look at the standard deviation. And this makes a lot of sense because the standard deviation measures the spread of the scores. So if you've got a really small standard deviation, that means that the scores are not very spread out at all. They're all really close together. And if they're close together, they're going to be really close to the mean. And that's going to make your curve taller and steeper because it won't be so spread out this way, and that's going to push it up. If you've got a large standard deviation, that means your scores are very spread out from the mean. And if they're going to be more scores spread out, that makes the top of your curve shorter. Does that sort of make sense? Now, when we measure something, the relative frequencies are all going to add up to a certainty. Now, we've already seen that when we graph a probability density function with continuous data, the area underneath the curve gives us information about the probability of that range of values occurring. And the same thing happens here with normal distributions. So whether a curve is taller and steeper or shorter and flatter, it will tend to still have that same area underneath the curve. So if the area under the curve is going to be 1, then if we've got a lot of the scores really close to the mean, then it's going to push that area and make it actually taller. And if the scores are further away from the mean, it will stretch the curve out, but since there's only a certain amount of area to play with, it will also squash it down. And that makes sense because if there's less scores close to the mean, then obviously the relative frequency of finding a score of that size is lower. Now, it's worth taking a moment just to consider the sorts of things that might have a normal distribution and the kinds of things that might not. So when you're looking at things in nature, we need to bear in mind that things do grow. And they start off small, and often they get to a point and then stop growing. So if you're measuring a bunch of things that are full grown, say, then it makes sense that they'll probably have a normal distribution. If you're measuring things and you've got a real range of ages in there, then the data might be a little bit skewed towards smaller things. So probably my example earlier with the lengths of the leaves on my lemon tree might not have been ideal if there's a whole heap of new leaves on that tree. But if I was to only include leaves in the survey that are over a certain age, that would take care of it. Similarly, if you're measuring something in humans, let's say you're looking at height, if you look at the height of a whole heap of 5-year-olds, that's almost certain to have a normal distribution. Similarly, the height of 10-year-olds is going to be normally distributed. The height of adults is going to tend to be normally distributed. But if you have a bunch of people and it's not a very big group, and there is a whole heap of kids in there and only a few adults, you can expect the data might not be normally distributed because the presence of all of those children is going to make a difference to it. So that's worth thinking about. But once you're looking at anything that's generally reached the end of its growing cycle, you'll find a normal distribution just about everywhere, whether you're measuring the lengths of people's little finger, the lengths of their ears, how wide their eyes are. If you're looking at full-grown adults or dogs or any species, you're going to find normal data everywhere.